In this lesson, we are going to learn how to use isolation forest to perform anomaly detection. So what is isolation forest? Isolation forest is a pretty new anomaly detection algorithm. Anomaly detection is the process of identifying unusual events that are potentially suspicious. The advantage of anomaly detection is that you don't have to have seen every possible unwanted event before detecting it. For instance, it is almost impossible to foresee all the possible types of financial fraud that are out there. But just through their unusual behavior, they will trigger a good anomaly detection algorithm. The idea behind isolation forest is that it is much easier to describe an anomaly than it is to describe an ordinary event. To give an analogy, imagine that you have a pond of fish, and all the fish are the same gray color, but one fish is red. When you describe that fish, you simply say the red one. But if you wanted to describe one particular gray fish, you better have a name for it, or some other special characteristic. Otherwise, describing it is very tedious and long-winded. Similarly, the way isolation forest works is that it uses trees to describe points, and those points that are easily described are anomalous. Those points that take a many very deep trees are normal points. So this number, the number of splittings and complexity that is needed to describe a point, is called the decision function, and that's the function we use to determine anomalous points using isolation forest. In this lesson, we are going to cover anomaly detection. Anomaly detection has the advantage over supervised learning in that it can find out things which you have not labeled before, which you have not seen before. So first, I'm going to create a data set. It's going to consist of normal observations and anomalous observations, and the two differ in arising from different distributions. Taking a quick peek, we can see that we've generated 2,000 normal observations, and then they are XY pairs sitting in the two-dimensional plane. And then the anomalous observations are only 200 in number. So next we're going to plot these so we can see what they look like. So I've labeled the normal observations in white and the anomalous ones in green. Some of the anomalous observations look completely normal, like the ones in the middle. So we can expect some mistakes for the algorithm since even the data itself is not clear. Next, I'm going to create a training testing split. I'm going to take some normal observations and some anomalous observations and put both of them into the training data set. This way I can guarantee that there is some training on the anomalous and some on the normal, which you'd expect in real life. Next, I'm going to instantiate an isolation forest model and fit it to the training data. The next thing we do is compute the decision function of all the normal part of the training data. You'll see why that is in a moment. So let's plot that. So note that any normal training point receives a score, and we just plot what the distribution looks like. Next, we're going to get the decision scores of all the anomalous training points and plot those on the same x-axis. What I'm going to do now is look for a way to separate the two, thus capturing the most normal points on one side and the most anomalous points on the other side. This separation will be how we determine if a new point is normal or anomalous. In other words, we compute its score and look if it's above or below the cutoff, and that is how we'll determine if it's anomalous or normal. By visual inspection, I've chosen 0.01 because it looked like a lot of the anomalies are on one side and a lot of the normal points are on the other side. The next thing I do is define some ways to score my model, false positive rate and true positive rate functions. A false positive is when a normal point is classified as anomalous. It's kind of like a false alarm. And a true positive is when an anomalous point is correctly labeled as an anomaly. So I'm going to compute these using the cutoff, we discussed earlier on the training set so I can see what the results would look like. And what we see is that it correctly captures 92% of anomalies and incorrectly captures about 1% of normal points. And then doing the same thing on the test set, we see that the results are pretty much the same and there's no overfit. So a successful anomaly detector. In the next lesson, we're going to talk about hyperparameter tuning. See you there.